We need to talk about what happened between October 29th and 30th, or more accurately, what didn't happen. And this matters because what's missing could rewrite everything we thought we understood about this interstellar visitor. 6 days after its closest pass to the Sun, on November 5th, 2025, astronomers pointed their instruments at the sky, just after sunrise, searching for something specific. They were looking for a tail. What they found was an absence so profound it broke the fundamental rules of cometary physics. How is that even possible? Here's the thing about comets. They're predictable. We've studied them for centuries. We know their behavior like clockwork. They approach the Sun, solar radiation heats their icy surface, frozen volatiles sublimate directly from solid to gas, and that material gets pushed away by radiation pressure, creating the iconic sweeping tail that can stretch millions of miles across space. It's textbook astronomy. It's what every comet does without exception. Except this one didn't. You've been following 3I Atlas since the moment it appeared in our solar system, watching as this 3.5-mile wide visitor from another star system made its dramatic approach toward our Sun. But what happened after its closest encounter reveals something so anomalous that even the world's leading astrophysicists are choosing their words carefully. When Harvard researchers start using terms like surprising and unexpected, you know something fundamental doesn't fit the equations. Between October 29th and 30th, 3I Atlas reached perihelion, the closest point to our Sun in its entire trajectory. At that moment, this ancient traveller was subjected to solar radiation, more intense than anything it had experienced in potentially billions of years of interstellar wandering. The physics here is straightforward and undeniable. Extreme solar heating equals massive outgassing, equals spectacular tail production. That's not theory. That's observable, repeatable, verified physics that governs every comet we've ever studied. Except that's not what happened with 3I Atlas. On November 5th, just days after emerging from the solar glare, the Arnaves Observatory in Spain captured what should have been the most dramatic images of this object's entire journey through our solar system. These aren't amateur snapshots. These are precision observations from a professional-grade facility using calibrated instruments. The images show the comet's nucleus surrounded by its coma, that bright fuzzy cloud of gas and dust that forms around the centre. The images are sharp, the images are clear, the data is unambiguous, but they reveal something that directly contradicts standard cometary behaviour. There is no tail. I want to be precise about what astronomers observed, because the details matter here. They saw a faint sphere of light. That sphere displays obvious cometary characteristics. Avi Loeb, the Harvard professor who's been analysing this object's behaviour through multiple observation windows, examined these November 5th images carefully. He noted that the coma's morphology, the actual shape and structure, doesn't look dramatically different from what Hubble captured months earlier, before the perihelion passage, before all that intense solar heating should have transformed this object into something spectacular. Think about what that means for a moment. This object just passed through the Sun's crucible. It experienced temperatures and radiation intensities that would vaporize most materials we're familiar with. It lost mass. Loeb's calculations, based on momentum conservation principles, suggest at least 13% of its total mass ejected during that close solar approach. That's not a small amount. For an object this size, we're talking about roughly 5 billion tons of material, according to Loeb's calculations. For any normal comet, that kind of mass loss creates something visually dramatic, something impossible to miss. Loeb himself worked through the mathematics. For a typical comet, this should have resulted in a massive coma with dust and gas that would have been pushed by the solar radiation pressure and the solar wind to the shape of a typical cometary tail pointing away from the Sun. A typical cometary tail, the kind we've photographed thousands of times, the kind that appears in every astronomy textbook. Instead, observers are documenting nothing, a sphere, a glow, an absence where physics demands presence. The Virtual Telescope project in Italy captured their own post-perihelion images on that same date, November 5th. Their report confirms what the Spanish observatory documented. The cometary diffuse nature of the object is obvious. The comet is definitely there. It's definitely visible. But observers are noting, with careful scientific language, that the structure doesn't conform to what physics predicts should happen after a comet sheds 13% of its mass during its closest solar approach. This isn't one telescope seeing something strange and jumping to conclusions. We're talking about an entire network of independent observatories, Spanish facilities, Italian robotic telescopes, Chinese space probes orbiting Mars, all converging on the same observation. The expected tail, the one that physics demands should be there, is absent. The Unaves Observatory didn't hide their images or claim ambiguity. They published exactly what they saw: a bright nucleus surrounded by a coma, with a conspicuous absence where every equation, every model, every historical precedent says a tail should exist. That image started circulating through the astronomy community immediately, through Reddit space forums, through X, through every channel where people who understand the implications gather. And the questions started cascading through those communities like a shockwave. Why no tail? That simple question has grown into something larger, something that touches the fundamental assumptions we make about how cometary physics works. If a comet can lose 13% of its mass during perihelion passage without producing a visible cometary tail, what does that tell us about what's actually happening inside this object? What mechanism could possibly explain this behaviour? Before we dig deeper into this mystery, if you're watching this on YouTube, hit the like button. Not for algorithm manipulation, though that helps, but because it signals that deep investigative science content, the kind that doesn't shy away from complexity or uncertainty, matters enough to support. I want to keep producing these detailed analyses. Drop a comment telling me where you're observing from, whether you're part of an astronomy club, whether you're tracking this object yourself, or whether you're just someone fascinated by mysteries that don't have easy answers yet. And if you haven't subscribed, this is your moment. What happens next in this investigation? What we learn about why this tail is missing? The revelations coming in December, when NASA finally releases their higher resolution data? You're going to want notification when I break down those findings, because this story is far from over. The question sitting in front of the entire astronomy community right now is deceptively simple, but profoundly challenging. How do you lose 13% of your mass during the most intense thermal and radiation environment in your trajectory, and produce absolutely nothing that resembles a cometary tail? That question doesn't just challenge our understanding of this specific object, it challenges our understanding of cometary physics itself, and that's exactly why we need to look at the science behind what should have happened versus what actually occurred. Let's talk about the physics underlying this mystery, because this is where the impossibility becomes mathematically quantifiable. When a comet approaches the sun, solar radiation doesn't just warm the surface like sunlight heating pavement. It penetrates deep into the nucleus. The frozen volatiles buried inside, water ice, carbon dioxide ice, methane, ammonia, all these materials locked in solid form for potentially billions of years, they undergo rapid sublimation. They transition directly from solid to gas without passing through liquid phase. This happens explosively. We're describing phase transitions driven by radiation that heats these materials to temperatures hundreds of degrees above absolute zero in a matter of hours or days. Avi Loeb, working from his position at Harvard's astronomy department, calculated the mass loss for 3I Atlas using straightforward momentum conservation principles. His mathematics isn't speculative. It's based on observable changes in the object's trajectory, changes that require mass ejection to explain. The number he arrived at, more than 13% of the comet's total mass lost during perihelion passage. 13%. To put that in context, if 3I Atlas has a nucleus roughly 3.5 miles in diameter, and that's our best estimate combining data from multiple spacecraft observations, and if we assume density similar to other cometary nuclei we've studied up close, we're discussing total mass depending on internal porosity and composition, ranging from several tens of billions of tons to possibly 1 trillion tons. 13% of that mass means roughly 5 billion tons of material sublimated and ejected during those critical days near the sun. Now here's the comparison that should make any astronomer pause. A typical comet, something from our own Oort cloud that follows a long elliptical orbit around our sun, undergoes a completely predictable process when it loses 13% of its mass at perihelion. The solar radiation pressure, and understanding this is critical, doesn't just release the gas and dust, it accelerates those particles away from the sun. Photons carry momentum. When billions of photons per second strike gas molecules and dust particles, they transfer that momentum, pushing the material outward. This pressure is directional. The particles get accelerated away from the sun's center, creating a trajectory that forms the classic cometary tail, pointing in what astronomers call the anti-heliocentric direction. anti-meaning away from, heliocentric meaning the sun's center. The tail always points away from the sun, not because of the comet's motion, but because of radiation pressure. When hundreds of billions of tons of material get ejected and then accelerated by intense solar radiation pressure, the visual result should be unmistakable. Professional astronomers use words like impressive and dramatic to describe what should happen. We witnessed this with Comet Neowise in 2020, visible to naked eye observers across Earth. We documented it with Comet Leonard in 2021, producing tails that stretched across significant portions of the sky. 3i Atlas lost comparable or greater mass than those objects. It passed closer to the Sun during perihelion than many famous comets. Solar radiation intensity follows an inverse square law, meaning it increases exponentially as you approach the Sun. Closer proximity means stronger radiation pressure, which means more dramatic tail formation. Mathematically, logically, physically, 3i Atlas should have produced a tail that makes those famous comets look subtle by comparison. According to the images from Nave's Observatory, Virtual Telescope Project, and other facilities, it didn't produce any clearly visible tail structure whatsoever. So what are the possible explanations? Let's examine them systematically, because this is where scientific investigation separates from speculation. Theory 1. The tail exists, but we're observing too early in its development. Cometary tails form over time. The ejected material needs to accelerate away from the nucleus. The structure needs to develop and become optically visible. Perhaps what we're seeing in the November 5th images represents early phase development before the tail becomes prominent. This explanation is plausible on its surface, but here's the problem. 3i Atlas passed perihelion on October 29th through 30th. The Nave's Observatory captured images on November 5th. That's 5 to 6 days of development time. In 5 to 6 days, a typical comet that lost 13% of its mass should have developed a clearly visible, structurally obvious tail. Not a faint developing structure, but something unmistakable. The observers are describing a sphere, a radially symmetric structure. A developing tail would break that symmetry, would show a symmetry pointing away from the sun. This theory scores maybe 4 out of 10 for likelihood. Possible, but requires we accept unusually delayed tail development, which itself would be anomalous. Theory 2. The tail exists, but it's composed of particles too fine to appear visible in the wavelengths being observed. Cometary tails contain dust particles ranging from micrometers to millimeters in size. Smaller particles scatter light more efficiently in certain wavelengths, while larger particles dominate in visible spectrum observations. If 3i Atlas produced predominantly fine dust during its outgassing, perhaps the tail exists but isn't showing up clearly in optical observations. This is scientifically interesting because it would indicate compositional differences from typical solar system comets, telling us something about the planetary system where this object formed. But there's a significant problem with this explanation. We have observations across multiple wavelengths, not just optical. Spacecraft are observing in infrared, ultraviolet, and other spectra. If the tail existed but was invisible in optical wavelengths due to fine particle size, we should see thermal emission signatures in infrared data. We should see ultraviolet absorption or scattering. The multi-wavelength data doesn't appear to support a hidden tail hypothesis. This theory scores maybe 5 out of 10 for likelihood. Theory 3. The mass loss mechanism wasn't normal cometary sublimation. This is where we enter speculative but scientifically legitimate territory. What if the 13% mass loss Loeb calculated wasn't caused by passive solar heating and sublimation? What if the mechanism was fundamentally different? Suppose the object was actively ejecting material through some mechanism other than passive outgassing, directional expulsion, controlled venting, material ejection driven by internal processes rather than external solar heating. If an object were actively ejecting material in specific directions, not isotropically in all directions through sublimation, but vectorially through targeted expulsion, the ejected material could remain in regions where solar radiation pressure isn't sufficient to create typical tail structures. Alternatively, if the object was using energy to direct material away from radiation pressure vectors, the particles could avoid forming the classic cometary tail configuration. This explanation requires accepting some kind of active mechanism beyond passive physics. Loeb has discussed this possibility in his public communications, suggesting the data is consistent with active propulsion as one potential explanation. I need to be absolutely clear. Loeb is not claiming proof. He's identifying a hypothesis that fits the observational data. The broader peer-reviewed scientific community hasn't reached consensus on this explanation, but it remains on the table as an investigative direction worth pursuing. This theory scores perhaps 6 out of 10 for fitting the available data. It explains the missing tail, it explains the mass loss, but it requires accepting that something beyond passive cometary behaviour is occurring, and that's an extraordinary claim requiring extraordinary evidence. Then there's the institutional transparency dimension that's become part of this narrative, and understanding this context matters for appreciating what information we're still waiting to receive, and why that delay is creating additional speculation and anticipation in the community tracking this object's behaviour. Before we move next on international verification, I want to pause here. Which of these 3 theories do you find most compelling? Drop your answer in the comments, theory 1, 2, or 3, and tell me why. Your reasoning might reveal patterns we've all missed. The best investigations are community-driven. Something remarkable happened during 3i Atlas's close approach to Mars in early October. Something that reveals just how significant the scientific community considers this object. Multiple space agencies coordinated simultaneous observations from different platforms. NASA pointed instruments from Mars orbit. The European Space Agency contributed observations. The China National Space Administration directed their Tianwen-1 orbiter to capture images. This level of international coordination doesn't happen casually. Multi-agency observation campaigns specifically designed to study a single object from multiple perspectives indicate that institutions recognize they're dealing with something scientifically important, something worth dedicating limited resources and observation time to document thoroughly. On October 3rd, 3i Atlas passed within approximately 18 million miles of Mars. That proximity allowed Mars-orbiting spacecraft to obtain detailed images impossible from Earth-based telescopes. China's Tianwen-1 orbiter became the first to make those images publicly available on November 6th. Not NASA, not the European Space Agency. China released their observations first, and understanding why matters for comprehending the institutional dynamics currently shaping public access to data. NASA's Mars Reconnaissance Orbiter captured images using its high-rise camera, one of the most sophisticated imaging systems currently operating in space. The technical challenges NASA's team solved just to target 3i Atlas were extraordinary. The comet was moving at 129,800 miles per hour. Its nucleus is only 3.5 miles in diameter. From Mars orbit, tracking that target required switching systems designed for stationary planetary surface imaging to detect something moving rapidly and reflecting roughly 10,000 to 100,000 times less light than typical targets on Mars's surface. NASA accomplished that targeting. NASA captured images that reportedly offer 3 times the resolution of Hubble Space Telescope images, but as of November 7th, NASA hasn't released those images. The reason is bureaucratic, not conspiratorial. The US federal government shutdown that began October 1st continues. It's now officially the longest government shutdown in recorded American history. Federal employees who would normally process and publicly release these images are furloughed. The systems for public data dissemination are offline. Meanwhile, China's Tianwen-1 spacecraft used its high-resolution imaging camera to photograph 3i Atlas between October 1st and 4th. Lower resolution than NASA's MRO, but effective, and China made those images available to the global scientific community immediately. The China National Space Administration published a statement with their observations. Comet characteristics of the celestial body are obvious in the image, which is composed of the comet's core and its surrounding coma, with a diameter of thousands of kilometers. The core, the coma, diameter measuring thousands of kilometers. This description aligns precisely with what ground-based observatories documented in early November. The object displays a visible nucleus. The object shows a substantial coma. But China's images, like the ground-based observations, don't reveal a dramatic cometary tail structure. Here's why the international network dimension elevates this from interesting observation to verified phenomenon. You have independent institutions using different instruments, observing from different locations, capturing data in different wavelengths, and they're all converging on the same basic observation. Post-perihelion, 3i Atlas exhibits a nucleus and prominent coma, but not the tail structure that physics predicts should accompany 13% mass loss. The European Space Agency's Mars spacecraft contributed observations. NASA's surface rovers, Curiosity and Perseverance, pointed their cameras skyward during the October 3rd conjunction. ESA's ExoMars Trace Gas Orbiter added its imaging capabilities. These aren't instruments designed specifically for comet observation. These are Mars-focused platforms repurposed for this unique opportunity, because the close approach represented a rare observational geometry. On Earth's surface, independent observatories coordinated their observation schedules to capture pre- and post-perihelion data. Arnave's observatory in Spain, Virtual Telescope project in Italy with their robotic systems, amateur observatories from multiple continents, professional and passionate amateur astronomers essentially created an ad hoc global network specifically to document this object's perihelion behavior. Why would this level of coordination emerge? Why would governments and space agencies prioritize imaging a single comet? Why would independent observers across multiple continents synchronize their efforts? The answer: 3i Atlas was already exhibiting anomalous behavior before the missing tail mystery emerged. In summer observations, astronomers documented an anti-tail, material appearing to move toward the Sun rather than away from it. David Jewett from UCLA and his research team published findings documenting this rare anti-tail phenomenon. The observation was unusual enough to warrant peer-reviewed publication and international attention. Then researchers documented unexpected brightening patterns. 3i Atlas brightened as it approached the Sun far more rapidly than typical comets at similar solar distances. Qicheng Jiang at Lowell Observatory and Carl Battams at the Naval Research Laboratory published research noting that the brightening far exceeds the brightening rate of most Oort cloud comets at similar radial distances. Why would it brighten differently? Compositional differences? Behavioral differences? Something fundamental about this object that doesn't match our comet models? Recent observations from early November showed colour changes, a faint bluish hue developing. That represents the third distinct colour shift since initial observations began. Each colour change potentially indicates compositional changes, surface evolution, or processes we don't fully understand yet. All these observations, the anti-tail, the unusual brightening curves, the colour evolution, created a scientific context where the international community was already paying unprecedented attention. The missing tail after perihelion isn't an isolated anomaly. It's the latest puzzle in a sequence that hasn't followed standard cometary behaviour patterns from the beginning. The International Observation Network represents humanity's collective response. We need to understand this from multiple angles, with diverse instruments, from various perspectives. We can't rely solely on one institution or one nation's data. When China's Space Administration and NASA and ESA and independent observatories all examine the same object and report consistent observations, that convergence builds credibility. If only one observatory reported the missing tail, skeptics could reasonably question instrument calibration, data processing, interpretation methodology. When Chinese spacecraft, American ground-based facilities, European instruments, and Italian telescopes all observe the same basic phenomenon, skepticism must contend with convergent independent verification. The coordination itself carries significance beyond the immediate observations. Geopolitical tensions between the United States and China exist across multiple domains, including space program competition. Yet when examining 3i Atlas, both nations prioritized scientific understanding over institutional rivalry. NASA's leadership wants those MRO images in the public domain despite the shutdown. China's Space Administration released their Tianwen-1 data immediately. ESA contributed resources. This represents cooperation emerging from recognition that understanding an interstellar visitor transcends political boundaries. Multiple institutions obtaining similar results regarding the missing tail phenomenon adds investigative weight to the observation. Verification through convergent evidence from independent sources transforms observation from potential artifact into confirmed phenomenon requiring explanation. This is why Avi Loeb's assessments carry particular weight. He's not speculating in isolation. He's integrated into this observation network, examining the same data streams professional observatories are capturing, reading the same technical reports, maintaining communication with researchers at multiple facilities. His assessment that the appearance is surprising, that expected tail formation based on 13% mass loss should be massive and obvious, comes from someone embedded in the actual observational community analysing real data. When institutional networks align around investigating a mystery, it validates that the mystery is genuine, that it's worthy of serious scientific attention and resource allocation, and now we're approaching the moment when that investigation might yield the clarity everyone's been anticipating, or might deepen the questions even further. So here we stand on November 7th, 2025, with a documented phenomenon that current cometary physics hasn't adequately explained. We have converging observations from multiple independent institutions spanning 3 continents and Mars orbit. We have a Harvard astrophysicist characterizing the behavior as surprising. We have 13% of a billion-ton object's mass unaccounted for without corresponding tail structures. And we have NASA's highest resolution images still locked behind government shutdown bureaucracy. What happens next determines whether this becomes a solved mystery or a paradigm-shifting observation. December the 19th carries observational significance. That date marks improved viewing geometry as 3i Atlas emerges more clearly from solar glare. Ground-based telescopes will have better angles. Illumination geometry shifts, potentially revealing structures or details obscured in November observations. December 19th represents when we might definitively determine whether tail development occurs post-perihelion or whether the absence persists, confirming this behavior as genuinely anomalous. Whenever the government reopens and negotiations continue toward potential resolution frameworks, NASA will release the Mars Reconnaissance Orbiter images. Those images could clarify nuclear structure revealing how mass ejection occurred. They might show visible gas or dust jets pointing in specific directions. They could support one competing theory or introduce entirely new puzzles. The temporal gap between observation, the October 3rd Mars conjunction, the October 29th through 30th perihelion event, the November 5th post-perihelion ground observations, and the anticipated NASA data release creates authentic narrative tension rather than manufactured suspense. We genuinely don't know what those higher resolution images will reveal. The observation network continues accumulating data. Our Nave's observatory continues imaging. Virtual Telescope Project maintains their observation campaign. Observatories worldwide add data points. The cumulative picture might reveal patterns individual observations miss. But let me be transparent about what we definitively know versus what remains speculative or under investigation. We know with certainty 3i Atlas reached perihelion October 29th through 30th. Post-perihelion observations from November 5th show nucleus and coma but no prominent tail. Avi Loeb calculated over 13% mass loss based on momentum conservation mathematics. For typical comets, this mass loss produces visible tail structures. Multiple observatories including Spain's R Naves, Italy's Virtual Telescope Project, and China's Tianwen-1 converged on similar observations. NASA's MRO captured higher resolution images currently unreleased due to government shutdown. What remains speculative? Whether tail exists but hasn't become visible yet. Whether dust composition affects tail visibility in ways we haven't accounted for. Whether 3i Atlas's mass loss mechanism involved something beyond passive sublimation. What the MRO images will ultimately reveal. Whether this represents genuinely anomalous physics or unusual but explainable cometary behavior. Loeb suggested the data is consistent with active propulsion, that directed mass ejection rather than passive sublimation could explain observations. This speculation is rooted in mathematical calculations and observational data, not unfounded conjecture. But consistent with active propulsion differs fundamentally from proof of active propulsion. The data is simultaneously consistent with other explanations. Some explanations simply require more unusual circumstances or mechanisms than others. Here's what I genuinely want to understand, and why I'm asking this community specifically. What am I missing? This community includes amateur astronomers who've studied comets for decades. Professional researchers following 3i Atlas through institutional channels, data analysts and physicists and engineers who recognize patterns from different perspectives, people from different countries with diverse scientific traditions and insights. If you have theory explaining the missing tail, share it. If you've encountered research addressing this question, link it. If you work at an observatory with insights about post-perihelion comet behavior, contribute that perspective. If you believe the NASA images will reveal something specific, let's discuss what and why. Investigations advance faster and become more rigorous when multiple minds engage them seriously. The observation network of telescopes and spacecraft tracking, 3i Atlas demonstrated that principle. Distributed investigation works. I'm extending that principle to this community. This mystery isn't exclusively for Harvard professors or professional astronomers to solve. It's open to anyone curious enough to engage seriously. December carries weight. December 19th. Continuing observations, NASA's eventual data release. Depending on what emerges, this story might shift dramatically. We might achieve clarity explaining the missing tail definitively. Or we might discover the mystery deepens, requiring additional investigation and potentially new theoretical frameworks. Either outcome requires you stay engaged. Subscribe to receive updates when new data arrives. Engage with the community enough to contribute your perspective when developments occur. Think about these questions now, so when new information emerges, you can participate in understanding what it means, rather than passively receiving interpretations. This is what real-time science investigation looks like. Not textbook conclusions already written and polished. Not solved mysteries presented retrospectively. Actual uncertainty. Actual questions. Actual global coordination attempting to understand something that doesn't fit existing frameworks comfortably. 3. iAtlas travelled from another stellar system. It journeyed billions of years through interstellar space to reach our solar system. Now it's passing through, showing behaviours we don't fully comprehend. Perhaps that's not coincidental. Perhaps interstellar visitors by their very nature challenge our locally derived understanding. Or perhaps we're simply encountering something genuinely rare, and science is doing exactly what it should. Noticing anomalies, investigating carefully, letting data guide conclusions rather than forcing conclusions onto data. November the 7th, 2025 marks the moment we collectively asked, why is that tail missing? We still don't have definitive answers, but through continued observation, rigorous analysis, coordinated international scientific effort and engaged community participation, we will understand. The question is what that understanding will ultimately reveal about this visitor from beyond our solar system. If you think you have insight into this question, share it in the comments. Tell me what you believe is actually happening with 3iAtlas. Tell me what you expect NASA's images to show. Tell me if you've been observing this object yourself and what you've noticed. Subscribe because December will be critical for this investigation. Hit like if deep investigative science content matters to you. And if you know someone fascinated by this interstellar visitor, share this with them. Right now, we're witnessing a mystery the entire world is investigating simultaneously. That's extraordinary. Let's understand it together.